In this lecture, you will see the basic principles and applications of cell memory alloys. This left figure shows the cell memory alloy instance used for operation, and right figure cell memory alloy wings is used in airplane. The aircraft took off with its wings 0 degrees in flat condition, so 0 degrees diffraction, keeping them level during takeoff. So level during takeoff. In order to adapt to various flight conditions and improve aerodynamics, the wings were thermally activated cell memory alloys folded at various angles during the flight. So the wings folded at a certain angle to improve the aerodynamics and to adapt various flight conditions. Ordinary metals and alloys can never return to their former shapes after being permanently altered by an external force. However, permanently altered cell memory alloys can be heated back to their original shapes. So ordinary metals and alloys is permanently deformed by external force. So permanently deformed by external force and never return back to the original shape, even if we heated these alloys. However, cell memory alloy is permanently deformed here. So this deformed cell memory alloy can be back to the original shape by heating. The cell memory alloy has its own set of temperature requirements for returning to its previous shape. So this temperature is referred to as transformation temperature. So if we increase the temperature of the permanently deformed cell memory alloy up to the transformation temperature, then this cell memory alloy will be back to its original shape. Other unusual alloys are known as superelastic alloys. When external force is released, these alloys instantly return to their previous forms. So if we use external force, then this superelastic alloys is deformed. But if we remove the external force, then this superelastic alloy instantly return back to its original shape. So this is called superelastic alloys. So these figures depicts the responses of various materials to the external force. Now let's see what happens if we make the coils using metals, same of the alloy, and superelastic alloys. If we extend this coil using external force, then these coils are permanently deformed. Okay? So this is permanently deformed. So external force is removed, then the metal and the alloy is permanently deformed. So still the same shape, but the superelastic alloy, if we remove the external force, then this form returns to its original shape. This one. Okay, so superelastic alloys has this kind of property. Now, if we heat the metal's coil, but the metal coil retain its permanently deformed shape, even if we heat up this coil, so it still remains in the same shape. However, same memory alloy coil, even if this coil is permanently deformed by external force, but if we heat this coil above the transformation temperature, then this coil returns to its original shape, this shape. That is the property of the same memory alloy. Same memory alloy, same memory behavior is observed in alloys with a thermoelastic martensite structure below a particular characteristic temperature. An external force can easily deform the alloy in this martensite. It returns to its original shape when the temperature is raised above a certain characteristic temperature, transformation temperature, despite being permanently deformed. The original structure of the Sway-Mobley alloy is austenite, which is a rigid crystalline solid. The zigzag patterns in the thermoelastic martensite structure allow the alloy to be easily deformed even by a small external force when it is in this state. So you can see here in the figure, this figure shows the zigzag patterns, and so this alloy change its shape easily by a small external force. But if we heat up this alloy above the characteristic temperature, transformation temperature, then this deformed alloy return back to its original shape. So that is the characteristic of the same memory alloy. The alloy in the martensite structure returns to its original state of austenite structure as the temperature increases. So this figure shows the microscopic martensite structure of nickel titanium alloy. Left is twinned and right is the twinned figure. There are four different temperatures for cell memory behavior. The first MS, which is the martensite start temperature. So this MS. So there's no martensite. So percentage of martensite at this temperature is 0. The martensite structure begins to appear in the alloy of the austenite structure at this temperature. So it starts to appear at this temperature. So we call this martensite starting temperature. The martensite finish temperature, MF, is the second characteristic temperature. So at this temperature, alloy consists of all martensite structure, so 100% martensite structure. So this is called the martensite finish temperature. So martensite start temperature, there is zero martensite structure, but at the martensite finish temperature, all structure consists of the martensite. At MF, martensite finish temperature, the alloy's structure totally changes to martensite structure as the temperature decreases. So at this temperature, so if we reduce temperature, then at this temperature, the alloy consists of all martensite structure. The alloy is shown in the figure is made up of a mixture of the several martensite variants. These figures, due to the fact that the borders of these martensite variants can be altered by small force, so the alloy is easily deformed. So this structure can be easily deformed by small force. So if we increase the temperature, then austenite start temperature, austenite and at this temperature, austenite structure is 0, but at the austenite finish temperature, the alloy consists of 100% of austenite state. That means 0 martensite state structure. So at this temperature, there is no martensite structure in the alloy. But at this temperature, 100% of the alloy consists of 100% of martensite state structure. So there is no austenite structure at this temperature. So this is called austenite starting temperature, and this temperature is called austenite finish temperature. So that temperature corresponds to the transformation temperature. As the temperature rises, the plastic deformed alloy reverse back to its original austenite structure. So at this temperature, the austenite structure begins to appear in the alloy at the third characteristic temperature of austenite start temperature AS. So at this point in the alloy, there is no austenite structure. 100% is martensite structure. So austenite starting temperature. At the first characteristic temperature of the austenite finish temperature AF, the alloy totally recovers to its austenite structure. So at this temperature, there is no martensite structure, 0% of martensite structure. That means our structure is the austenite structure. Hysteresis can be seen in this swell memory behavior. So see, we have the hysteresis behavior. That is, the alloy does not take the same path when the temperature is raised and lowered as seen in the figure. In the transformation hysteresis, the delta T varies depending on the type of cell memory alloy. This figure shows the thermoelastic martensite structure. Let's look at how a cell memory alloy deforms as a function of temperature and external force. The alloy is in the austenite structure above austenite finish temperature AF. The alloy transforms into the martensite structure as the temperature drops below martensite finish temperature. During this transformation, the macroscopic morphology does not alter. Only alloy's internal microscopic structure is changed. So we cannot see any structure change in the macroscopic view, but the inside microscopic view, we can see the structural change inside the alloy. The thermoelastic martensite structure is made up of platelets that are alternately sheared. As shown in the left figure of the figure below, these platelets have herringbone compression. It is said that the alloy is in the twinned martensite structure. A small external stress can easily transform the twinned martensite face into the twinned martensite, the face as shown in the right figure here. So this twinned face can be easily transformed to the detwinned form by small external force. If the temperature is not raised above AF, the alloy will remain in this detwinned martensite phase. However, the alloy recovers to its original state of austenite structure as temperature rises above AF, austenite finishing temperature. This figure shows these procedures. So at this temperature, the alloy has austenite structure, and we lower the temperature below martensite finish temperature then this alloy has twinned martensite structure. And if you apply small force to this alloy, then this alloy deformed. So we can have the twinned martensite structure. So in this if we do not heat up the alloy, then alloy remains in this detwinned martensite state. But if we heat up the alloy, then this alloy recovered to its original shape, austenite to face. The same memory alloy is in the state of austenite. However, below a certain transformation temperature, it exists in the martensite structure. So this is MF, right? Martensite finish temperature. It exists in the martensite structure. Okay, this structure, which is easily deformed by small external forces. So as we have the twinned martensite state, then heating the alloy above the transformation temperature, on the other hand, quickly restores the alloy's original austenite structure. So if we heat up the alloy returns back to its original austenite structure. This shows one example of the same-body alloy property. So if we use that same alloy to obtain this kind of shape, so that's ice. And if you lower the temperature below the martensite finish temperature, and then using external force, we can deform this shape. But if we heat up, then this deformed structure back to the original shape of the structure, ice structure. So this figure shows the how the same-body alloy is transformed to its state by heating. Let's look at how the superelastic alloy responds to external force and the temperature. A small external force above austenite finish temperature can cause the superelastic alloy to deform into a martensite structure. So above austenite finish temperature, if you apply some force, then the austenite structure you change it to the twinned martensite structure. The alloy of nickel and titanium exhibits 8% strain during this deformation. Because the austenite structure is a stable phase above AF. Okay. So austenite structure is the stable phase above this temperature. So we stay the temperature above the austenite finish temperature. Then when the external force is removed, the alloy returns to this austenite to phase. So this figure shows this procedure of the superelastic alloy. One-way and two-way shape memory alloys are the two types of shape memory alloys. Only heating causes the one-way shape memory alloy to exhibit the same memory behavior. By increasing the temperature above AF, the deformed martensite alloy can return to its original shape. However, cooling the one-way shape memory alloys to a temperature lower than martensite finish temperature will not allow it to resume to its deformed shape in the martensite phase. So there is a properties of one-way shape memory alloy. The two-way shape memory alloy, on the other hand, can resume to its deformed shape in the martensite phase by decreasing its temperature below MF. However, the majority of shape memory alloys have one-way shape memory properties. However, some have the two-way shape memory properties. So this is the one example of the shape memory alloy coil. And this is the spring. Using a spring, this spring, one-way shape memory alloy can be converted into a two-way shape memory alloy, as shown in this figure. As the temperature rises over the transformation temperature, the shape memory alloy coil extends to the right to its original length. So original length is the extended coil, this much, for example. So this length is the original length of shape memory alloy coil. So if we increase the temperature above the transformation temperature of this shape memory alloy coil, then this coil expands to the right to its original length. Then the spring, so if we lower the temperature below the martensite finish temperature, this deformed shape memory alloy will not back to the deformed state, because that is one-way shape memory alloy. So once this shape memory alloy return back to the original length, it cannot be back to the deformed state as we decrease the temperature. So there is the property of the one-way shape memory alloy. But if we use a spring here, then spring then contracts the shape memory alloy coil to the left as temperature drops. So as the temperature drops, the spring move back to this shape memory coil to the deformed state. Since the temperature is below the martensite finish temperature, so this shape memory alloy can be easily deformed by external force. So external force is given by this spring. So the spring move this shape memory alloy to deformed state, and we heat up this shape memory alloy again. Then this shape memory coil move back to the original length, so it will expand to the right. but if we temperature, if we decrease temperature below Martensite finish temperature, then the spring forces the cell memory coil to deform the state again. Okay, so in this way, this one-way cell memory alloy can be used as a two-way cell memory alloy. So the cell memory coil acts as a two-way cell memory alloy in this manner. So using the spring, we can make the one-way cell memory alloy to the two-way cell memory alloy. Now let's see the cell memory alloy materials. Reed discovered the cell memory effect in AU cadmium alloy in 1950. In 1964, the United States Office of Naval Research, ONR, developed the nickel titanium alloy, which they named nitinol. Because it was so easy to process, it was used to make coils and other complex shapes. In the 1970s, after basic mechanism of cell memory alloy was clearly understood, significant progress in the cell memory alloy research was performed. In some situations, the superelastic effect has also been linked to the cell memory effect. Following that, various cell memory and superelastic alloys were developed and are now widely used in industry. This table shows the types of cell memory alloys, various types of cell memory alloys. This is silver cadmium and gold cadmium, copper, aluminum, nickel, nickel, aluminum, nickel, titanium. So there are several alloys to show the cell memory behavior. And this column shows the composition ratio. Cadmium is 44 to 9%. Then if we change this range for cadmium, then transformation temperature is changed in this range. So you can see here we changed just 4% of cadmium, but the transformation temperature we changed around the 240 degrees. So if small change of the composition ratio, we can see the big change in the transformation temperature. Okay. So the same behavior can be seen for other alloys. So if you change a very small amount of component material, then you can see the very large change in the transformation temperature. In industry, titanium nickel titanium is widely used, and here we change the composition of the nickel, changed from 94 to 51%, just a 2% change. Then we have here 150 degrees change in the transformation temperature. So you can see the very little change in the composition gives a very large change in the transformation temperature. Now let's see the applications of cell memory alloys. The majority of cell memory alloy behavior is one way, as mentioned before. This means that if the deformed cell memory alloy is heated above the transformation temperature, it returns to its original shape, but the alloy does not return to its transformed state when the temperature is lowered. We already mentioned this. If spring is used, the cell memory alloy's unidirectional behavior can be changed to bidirectional behavior as shown in the figure below. So we already explained this, but let's see this again here. An external force shrinks the cell memory coil to the left below the cell memory alloy transformation temperature. If the temperature of this shrunk SMA coil is raised above the transformation temperature, it will revert to its original shape. So to the right. As a result, the cell memory alloy coil shifts to the right. Even when the temperature is decreased again below the transformation temperature, the cell memory alloy coil retains its original shape without spring. Okay? So if we do not have a spring, the deformed cell memory alloy coil will not go back to the transformed state. However, due to the spring, the cell memory alloy coil in the Martensite state can move back to the left when the temperature is lowered again. Okay? The cell memory alloy coil is easily deformed by the spring's force if it is in the thermoelastic Martensite state. As a result, cell memory alloy coil returns to the left due to the force given by the spring. A spring can change cell memory alloy's unidirectional one-way behavior to the bidirectional behavior, two-way behavior in this way. So change of the cell memory alloy from one-way behavior, unidirectional, to bidirectional, two-way behavior by using a spring. Cell memory alloys are being utilized in planes, heat engines, robots, medical equipment, eyeglass frames, and other applications. Cell memory alloys are commonly used in airplanes and submarines to connect pipe or brace. The figure shows how a cell memory alloy O-ring is utilized to firmly join two pipes. So the two pipes is connected by O-ring. The O-ring's diameter is the same as that of pipe. So diameter of this pipe is the same as the O-ring's diameter. So we cannot put this in. However, by expanding the O-rings, it can be fitted between two pipes. So below Martensite finish temperature, then we can extend this O-ring to fit the pipe. So by expanding the O-ring, it can be fitted between the pipes. Okay, so we can put this O-ring into the two pipes. The O-ring then returns to its original shape and firmly joins the pipes after being heated. So if you heat, then this O-ring return back to the original shape and tightly join two pipes. If we add teeth, so this kind of teeth to the O-ring, the teeth will bite into the pipe and create a tight seal. Okay. As shown in the right figure, this figure, a same memory alloy plate can be utilized in surgery to bond the shattered bones. So shattered bones connected by same memory alloy plate. We can return the expanded plate to its natural shape and tightly connect the damaged bones by heating the plate following surgery. So after surgery, we heat up the plate, then the plate go back to original length, and this plate tight two shattered bones together. Crowning of teeth is, as shown in the figure below, follows the same concept. So this crown is the same diameter of this tooth, and below the martensite finish temperature, then we can expand this crown to fit into the tooth, and then we put this crown to the tooth and then heat up. Then this move back to the original shape and tightly bond to the tooth. Okay. Same memory alloy can also be used to make fine wires for braziers. So this inside brazier, these tiny wires are in it, located. The wires in the brazier wrinkle when washed in a washer. However, because the wire's transformation temperature is close to that of the human body, the wires return to their original shapes when worn, so we tightly fit to the breast. The application of the same-mobile alloy spring to control the water temperature is shown in the figure below. This figure. The desired temperature is set at 40 degrees in the figure. So the spring set to the 40 degrees. The same-mobile alloy spring returns to the original shape to the right to shut off the water flow, hot water flowing. If the temperature rises above the set temperature, shutting off the hot water flow. The bias spring pushes the same-mobile alloy spring to the left if the water temperature is forced below the set point, allowing hot water to flow again. So temperature is lowered, then this spring push back the same-mobile spring to the original position to the left. This is super elastic alloy applied to the eyeglass. To expand the narrowed blood vessels, same memory alloy stents are utilized. So this stents, so crimped to artery diameter. That's the original shape. These same memory alloy stents are put into the veins after being crimped to the artery diameter at low temperature. So we shrunk this stent to fit the artery diameter and put here and then heat up by the blood flow. Then it will expand to the original shape, and the blood can flow through the vessel. They are then released as the blood raises their temperature to that of the human body. Same of the alloy stents have transition temperature that are set to match to the body temperatures. Right.